talk of the day by Professor Nina Balcan from Carnegie Mellon. Nina is a world expert at the intersection of several areas, and she's going to be talking about machine learning for algorithm design. Nina?
Yep. Can you guys hear me?
Yes.
Yes.
Okay, cool. So yeah, so I'll talk about machine learning for algorithm design. So I guess as Gabi said, so I worked in several fields, including machine learning, theory computing, algorithm game theory and economics, and I often use machine learning lenses to address kind of challenges in other areas. And the talk today is exactly doing this, using learning theory lenses to kind of put data-driven algorithm design on solid theoretical foundations. Okay, cool. And let me start with a high-level overview of this talk. So as probably everybody here knows, the classic approach to analyzing and designing algorithms assumes a couple of things. First of all, it assumes that the algorithm we design for a given, say, combinatorial problem is hand-designed. So you have a brilliant scientist, sits down, thinks hard about an algorithmic problem, has a stroke of genius, and comes up with an algorithm, for solving the underlying problem. So that's one assumption made by the classic approach. And another another assumption is that from an analysis point of view, we often care about worst case analysis. So in particular, we impose that the algorithm that we design for the given problem must succeed even for solving just a one-time worst case instance of the problem about which the algorithm designer has absolutely no information at all. Okay, and this has been the kind of so this classic approach, as you all know, has been the backbone of algorithmic research in the past 50 years or so. And when it's possible to do this, to have hand-designed algorithms that have great worst-case performance guarantee, this is awesome. It's great. However, unfortunately, many algorithmic problems are hard within the classic framework. So it's hard to get good worst-case guarantees by hand-designed algorithms. And examples of kind of hard problems in the classic frameworks include clustering problems, partitioning problems, pricing problems, auction design problems. And in fact, most problems are really hard in the classic framework. Okay, and this is why in recent years, across several applied areas and also in theory of computing as well, there has been a lot of interest in somehow using machine learning for algorithm design, right? So machine learning has been so successful everywhere. Let's try to use it for algorithm design as well, right? And this is actually, if you think about it, quite natural, trying to do so. Why? Because, for many algorithm problems we might want to solve, often we have various types of, algorithms we might try to use, first of all. And second, we often have access to samples of typical instances coming from a domain, right? So, we also often have access to data, right? So if in the case where we have access to typical instances of the problem that you might want to solve coming from a specific domain, it does make sense to then use learning to learn an algorithm that does well on the instances coming from our specific domain and not care so much about worst case instances. Okay, and indeed this idea, it's very natural. Actually, people have looked at it in AI, artificial intelligence, computational biology, and game theory starting around 2000. And as you can see in my graph, there has been an explosion of work recently. However, most of this work has been empirical, so no performance guarantees, right? And so the beauty of the classic algorithm design and analysis is that we have strong performance guarantees on like the objective at hand, running time or solution quality, whatever, right? But these data-driven algorithms have not had, up until very recently, such formal guarantees, like provable guarantees. And in the past few years, 6 years or so, with my students and collaborators, we have basically developed a series of results that help us put data-driven algorithms on solid theoretical foundations. And we have had a variety of case studies and also some general principles that can hopefully help others study data-driven algorithm designs. And so what I want to do today is to tell you a little bit about this. And by the way, this is a work joined with several of my students and collaborators. And when I'm going to mention a specific result, the name of the collaborators will be acknowledged on the specific slide for the specific result. Okay, cool. So this is the high-level overview. Now let's become a little bit more precise. I'll be thinking about machine learning for algorithm design or data-driven algorithm design as introduced from a formal point of view in a paper by Rishi Gupta and Tim Ravgarden in ITCS 2016 and SciComm 2017 paper. So here is the setup. So we fix the problem that we want to solve, and maybe it's clustering or your other favorite algorithmic problem. So we fix that problem, and then what we do also fix a large parametric family of algorithms for that problem. Okay, and then what we do, we're going to take samples of typical instances coming from our domain, and then we want to use this sample of typical instances to find an algorithm from this large fixed family of algorithms that does well on new instances coming from the same domain. Okay, and to make this a bit more concrete, let me give an example of a problem we might want to solve. So let's think, for example, for simplicity about clustering, say objective-based clustering, right? This is what people like to study in theory of computing. So, for example, let's think about K-means clustering. Okay, so here we have as input a set S of objects and also a distance function specifying the distance between any of these two objects. And then the goal here is to output a partition of the given set of objects and centers for each part of the partition in order to minimize the sum of all points of the distance squared to the nearest center. Okay, that's K-means clustering. There are other related objectives like K-median, K-center, and it turns out that they're all be hard to optimize, right? So they are hard within the classic framework, and so it's natural to try to think about solving them in a data-driven way. This is so this is kind of objective-based clustering viewpoint. But I don't know if there are learning people here in the audience, but if you're a machine learning person, you might be more familiar with something like unsupervised learning formulation of the clustering problem, where what you assume you have as input again a set of objects and the distance function specifying the distance between any of those two objects. And what you want to do, you want to output kind of some sort of clustering, a partition of the data that minimize some distance to some ground truth. So for example, I might want to learn to cluster documents the way Elena clusters documents. Yeah. So that's actually, that's actually a hard problem to even formalize. What do we even mean by that? So it's a very challenging problem. So it's again a perfect example of a problem that is hard in the classic framework. So it's good to try to solve it in a data-driven way. Okay, cool. So with this problem in mind, this is an example of a problem. Now, I mentioned, without going into a lot of details, now I mentioned when we think about data-driven algorithm design, after we fix our problem that we want to solve, we also need to fix a large parametric family of algorithms. And what could be a large parametric family of algorithms for the clustering problem? Again, I'm not going to go into the details right now, but at the high level, it could be something like we might consider an example could be a family of two-step procedures where if the first step does some sort of greedy linkage-based kind of clustering to put the data into a hierarchy, and then in the second step we do say dynamic programming to extract the best pruning to extract the partition. And such algorithms are fast, and you can have parametric families of such algorithms, and you might want to learn the best algorithm from the family for your type of data. Okay, so this is just an example of a problem to keep in mind. Now, with this example, let me kind of, at a more high level, describe how you can think about data-driven algorithm design as a statistical or distributional learning problem. Okay, so we first fix the problem that we want to solve, say clustering, or your other favorite problem. And then we also fix a large parametric family of algorithms for our problem, right? So, and this parametric family of algorithms could have, like greedy components, dynamic programming components, your favorite type of, algorithmic module. And this family could also be infinite. Why? Because some of these modules could have some knobs or parameters that we might want to tune. Okay. So we fix the problem that we want to solve. We fix a large parametric family of algorithms for our problem. And then what we assume that we're going to have a training set of typical instances for our problem coming from a specific domain that is given upfront. And mathematically, we'll assume that this training set of typical instances are drawn IID, so they're independent, identically distributed from some fixed unknown distribution over typical instances. Okay, so for example, for the clustering problem, if I'm trying to solve a clustering problem, this is how a training set of typical instances might look like. This is the first set of documents I might want to cluster, input one, a second set of documents I might want to cluster, and so on. And I have capital N such training instances, sets of documents I might want to cluster. And they can be unlabeled if I'm doing kind of objective-based clustering like K-means, or they can be labeled if I'm trying to do unsupervised learning and try to learn the way Elena clusters documents, right? Depends on the problem formulation. Okay. So now the goal is, so I fix the problem that I want to solve. I fix a large parametric family of algorithms for my problem. And I'm also assuming that I have access to a training set of typical instances of my problem coming from my domain. And now the goal is to use this training set of typical instances to come up with an algorithm from my family that does all our new instances coming from the same source as the training set of typical instances. So basically, I want to generalize, to find algorithms that do well on new instances I've not seen in the training set. And so, of course, like, how would I do that? The most natural approach would be to try to find an algorithm that does all over the training set of typical instances, and then to hope to then prove that it somehow generalizes. And so now a key question when you phrase this algorithm design as a statistical learning problem is this sample complexity question or generalizability question, right? Like, of course, if I have too few training instances, there'll be no hope for me to generalize and to find algorithms that do well on new instances. And so, but the more instances I see, the more likely it's going to be that I'll be able to generalize. Okay, and so then now a crucial question is what we call in learning theory, it's a sample complexity question, which asks how large should the training set of typical instances be in order to guarantee that if I find algorithms from my family of algorithms that do well over the training set of typical instances, those algorithms will also do well on new instances that come from the same source as the training set of typical instances. Okay, this is a key sample complexity question that we want to understand. Yeah, basically the generalizability of our data-driven algorithms. Now, to answer this question, luckily, it turns out that we can build on tools from statistical learning theory. So without going into too many details, we know from statistical learning theory that if the number of training samples we see in the training phase is roughly proportional to somehow the intrinsic complexity of the family of functions at hand over epsilon squared, then it's kind of roughly sufficient to say epsilon generalize, to get within epsilon or the best you can hope to get. What is this notion of, what do I mean by intrinsic complexity of the family of functions at hand? In our case, the family of functions at hand will be a family of functions induced both by our algorithms families and by the performance measure, like the loss function that we consider on algorithm. It can be runtime, solution quality, or your other favorite performance measure. Okay, and what are these notions of capacity of family of functions? So if you have seen learning theory before, you might, I'm talking about things like VC dimension, pseudo-dimension, real value analogs of VC dimension. And really what these intrinsic measures of complexity of a family of functions is trying to characterize, again, intuitively speaking, it's just trying to characterize the ability of the functions in my function class to fit complex patterns. Why? Because the more complex patterns I can fit, the more samples I need to generalize and to not overfit. Okay, and I'm gonna keep it at this level. So if you, what do I mean by intrinsic measure of complexity here? Okay, cool. So we can build on tools from statistical learning theory to try to analyze how many samples of typical instances we need to be able to generalize to find algorithms that do well on new instances that we've not seen in the training phase. But now the challenge is, that actually when you sit down and analyze them, the way I've done with my students, is that actually turns out that we cannot just rely on the existing tools in learning theory. So to analyze these notions of intrinsic dimension. Why? Because if we sit down again and analyze, it turns out that a lot of these functions that we care about coming from data-driven algorithm design, they are very volatile. So they will have many sharp discontinuities on many points, which is very atypical in functions that we typically analyze in learning theory. So that's a major challenge we have to handle. But these loss functions are very volatile, so we have to develop new tools to analyze the intrinsic complexity of the family of algorithms. But the first major challenge and the second major challenge is that we need to also design computationally efficient procedures, hopefully at the end, right? So we want not only to need few samples to generalize, but ideally we also want to be able to pick the algorithms from the family that does all our new instances coming from our domain in a way that is computationally efficient. Okay, so these are two major challenges that we have to understand. And, again, we have been doing this for several years now, and we were able to successfully answer these questions for several problems. And today, I'm going to tell you about one case study, so the clustering problem that I introduced earlier, and some general results, some general principles that we have extracted that hopefully are applicable much more broadly.
Sorry, could I ask a quick question?
Yes.
What is an example of a loss function? Does this depend on the family of algorithms? Is it a feature of the algorithm family or of the
It is. So it is in the end. So I'm going to go maybe, it is actually a feature of the algorithm family. An example of a loss function could be actually for the clustering, which I'm going to give next as an example, will be the performance measure, the quality of the clustering. Like we're gonna, so actually let me go, so actually that's perfect introduction to the next slide here. So I'm gonna now go on and give a concrete example. And here I'm gonna think about the clustering problem that I introduced earlier. And now I'm gonna consider a family of algorithms that are polynomial time by design. And what I'm gonna try to find is the algorithm that optimizes the solution quality. So I'm gonna try to find an algorithm from this family that has the best solution quality over my instances, like k-means clustering solution quality, or maybe distance to the ground truth solution quality. Yeah, this is what we've done here, but the theory applies much more generally. You had other examples where we fix family of algorithms that are not necessarily polynomial time, like solving mixed integer programming by a branch and bound, and then the solution, and then the loss function varies runtime. So like we had a bunch of variants in the various works. Okay, but to keep things simple, let's go back to the clustering problem. Then I'm going to be very specific here. Actually, the loss function is actually the solution quality.
Nina, there is also a question in the chat. Are also the family of algorithms hand designed or generated automatically in some way?
That's a great question. So far, they have been hand designed, but the next step would be awesome to maybe lift it up and to hopefully generate in a more automated way if possible. Yeah. So that's a good research question. So far, we were hand designed. So I still use my intuitions as an algorithms researcher to come up with family of algorithms and have reasons to consider them analytically. Yep. Cool. So going back to the concrete example. So let me go back to clustering. So as I mentioned, so here let's consider for concreteness a family of two. These are polynomial time algorithms. These are two-stage algorithms. So we first do some sort of greedy or linkage-based algorithm to link the data into a hierarchy or into a tree of clusters. And then at the end, we do a fixed algorithm on the top, say dynamic programming, to select a good pruning from this tree. So then the output, here is my output partition, the pruning from the tree. Okay, and actually both of these steps can be done efficiently in polynomial time. This is why these are types of algorithms used widely in practice in compile. Okay, and now, what do you mean? Actually, in case you've not seen them, or just to remind them, what do I mean by linkage? In our bottom-up procedures, so these are very simple procedures. So we start with each point in its own little cluster, and then we repeatedly merge the two closest clusters until at the end we have all the points, all the documents in one big cluster at the top, at the root. Now, what do I mean by two closest clusters? Because of course, different definitions of closest, different definition of distance between clusters lead to different algorithms. And here are a couple of examples that I teach in intro machine learning courses. So the first one is single linkage. Now we define the distance between two sets or between two clusters to be the minimum distance between points in those two clusters. That's one example of distance between two clusters. Another one is complete, a notion of distance between two clusters that corresponds to complete linkage, where now I define the distance between the two clusters to be the maximum distance between points in the two corresponding sets. Okay, so these are two examples of kind of notions of distance between clusters. There are others like average linkage, where you define the average distance and so on. And in fact, if you want, you can even put down a large parametric, infinite parametric family of distance functions, like basically, to interpolate between any of these classic linkage criteria. So here is one example that we analyze in our work. In a called 2017 paper. It was one of the earliest works we have in this topic. So here we define what we call the alpha weighted linkage kind of distance, where we interpolate linearly between single linkage and complete linkage. So basically we assume that there is some unknown parameter alpha that we can hope to tune on data, based on data, and then we define the distance between two sets A and B to be 1 minus alpha times the distance given by single linkage plus alpha times the distance given by complete linkage. Okay, so you can consider basically infinite parametric families of linkage procedures. And you might wonder, why do I do so? Well, isn't there a magic linkage procedure I can use that doesn't on all the data? And the answer is no. So we do have to really actually adapt the linkage criteria to the data. And here is basically a couple of I have on this slide a couple of like toy examples illustrating this. So say that you have two target clusters. Now this is instance one on the left. If these are the two target clusters, the red circle is one target cluster and the blue circle is another target cluster. Turns out if you analyze it and also run experiments, turns out that this is a very easy instance for single linkage. Single linkage will do great on this instance to recover the correct target clusters. However, it's very hard for complete linkage. So complete linkage will output a bad partition here. on this is for instance 1. For instance 2, you know, if which is on the right, what I have now is two kind of disks. So the green disk and the purple disk. Turns out that actually this is hard for single linkage. It will end up merging early on clusters from points from the two target clusters. So single linkage will do badly here, but complete linkage will do well here. So really, what I'm trying to show here also, you really want to adapt to the data. So there is no magic linkage criterion. Okay, and so now going back, so this is an example, like a concrete example of family, going back to the earlier question that I talked about. Well, if you have access to a training set of typical instances, can you hope to learn the best, say, linkage criteria for your type of data? And the answer is yes. And this is one of our earliest results on the topic. So what we're able to prove here is that the intrinsic complexity of the family of functions at hand here is not too large. It's only big O of log n, or n is an upper bound on the number of points in the training set, which then implies that, again, using still some statistical learning theory, we don't need too many samples to generalize. We don't need too many typical instances to generalize. And then we are also able to show here for this simple family that basically given a training set of typical instances like I have here, we're able to also show how you can find the best algorithm from the family kind of efficiently. By efficiently, I mean in a way that you can run large-scale experiments and show how well they do in practice. Not only polynomial time, but really scalable.
So what is n?
N is an upper bound on the number of points you might in any possible input instance. So for example, if I'm doing a clustering here, it's just an upper bound on the number of points I might have to cluster in at any moment in time. Yep.
So I mean, we're assuming that the dimension is log or like, oh, okay, maximum. So what kind of a dimension are we talking about?
So this is like a BC pseudo dimension. So formally it's the pseudo dimension, which is the real valued analog of BC dimension. Yeah.
And these are points in Rn or something like that?
Yeah, there are points in Rn. Yeah, actually all we need is a distance function. It doesn't have to be in Rn. All we use the fact that the distance, the original, right? So when you do linkage procedures, we assume that you have a distance function between the points. And all we assume it's just a distance function, doesn't even have to be in Euclidean space.
So data driven means that, I mean, you do have the family of algorithms, meaning that here you have the family of linkage functions that you're going to choose from. And
yeah, exactly.
Okay.
So I'm going to choose the linkage criteria, right, from, based on data. Basically, I have a training set of typical instances like I had here, right, on the pictorial on the slide. And exactly, I'm going to learn the linkage criteria in a data-driven way.
Okay.
To minimize the solution quality, essentially. Yeah. And why is this? Okay. And so again, like, here we show that the kind of the fact that the intrinsic dimension is small here of the corresponding family of functions. It means we don't need too many samples to generalize. It means I only log n over epsilon squared samples, a training set of typical instances in order to learn the best linkage criteria, basically. And again, this is, to be clear here, this is for the family of algorithms for this specific family of functions, parametric family of linkage procedures, because if you change the parametric family of linkage procedures, the pseudo-dimension might be different. And in fact, in our work, we had several such families of linkage procedures, parametric families of linkage procedures, right? This log n is for this specific family. Okay. Okay, and why is, again, like, and why is hard to prove, why is not trivial to prove such pseudo-dimension based bounds? Well, because again, like as I mentioned earlier, kind of the loss function, the induced loss function can have many sharp transition boundaries. So, and intuitive here for these linkage algorithms is easy to see because, small changes to the parameters of the clustering algorithm can lead to radical changes in the tree of the order clustering produced. Why? Because, if you fix an instance, a single change, if you change the parameter, then it can lead to a single change to an early decision made by the linkage algorithm, but that can snowball and produce much larger changes later on. So you can get a totally different clustering at the end by slightly varying the parameter alpha. Okay, so that's an issue, that kind of the corresponding loss functions, if I fix an instance of the problem and vary the parameter, the corresponding loss functions can have many sharp transition boundaries. And, and if they become very crazy, it's hard to prove any generalizability, But luckily, what we're able to show for this simple example is that for this alpha-weighted linkage family, or interpolated linearly between single linkage and complete linkage, what we're able to show is that if we fix an instance of the problem, vary the parameters, kind of the cost function, sure, will be piecewise constant, will have sharp transition boundaries, but with not too many pieces. We're only going to have polynomial number of pieces, in particular, n to the 8 pieces. Okay, so that's what saves us. So, again, intuitively speaking, so why is this the case is, I'm not going to go for proofs here, but why is it the case? What these sharp transition boundaries correspond to, like really correspond to roots of linear equations defined by 8 points, where we prefer to roughly merge one pair of clusters to another pair of clusters. So we can kind of use the structure of the linkage family to then argue that, again, if I fix an instance of the problem, vary the parameters, kind of the corresponding cost function will be a piecewise constant with at most n to the 8 pieces. There are at most n to the 8 possible trees really produced in the end over the given instance. Okay, and why is this useful? And here this will be assuming that you know a little bit about VC dimension. So if you don't know, don't worry about it. So, you know, if you know from VC dimension learning theory, you know that what's the VC dimension is the cardinality of the largest set of instances that you can basically shatter, on which you can achieve an exponential number of behaviors as you vary the parameters of your function class. And so because of this structure result that shows that if I pick an instance of the problem and vary the parameters, I can have at most n to the 8 pieces on the induced loss function, then we can show that we can have an exponential number of behaviors on at most log n different instances. Okay, and then that implies that the absolute dimension is not too large, it's only log n, so therefore we get a small sample complexity. Okay, so here I'm assuming some knowledge of learning theory, but don't worry, this is just a high-level idea if you're not familiar with it. Okay, I prefer to give an overview talk, by the way, instead of going to a technical talk and only presenting one result. I just chose to give an overview talk and give you a flavor of the results we develop in this field. Okay, so it turns out the intrinsic complexity is not too large, so we don't need too many samples to generalize for this alpha-weighted linkage family. But what's nice actually about this family is that actually we also have an efficient procedure for finding the best algorithm from the family, you know, given a trained set of typical instances. And so this is an idea that one of my former students, Travis Dick, had. So it turns out that you can, like, how would you do it at a high level, basically? So given a trained set of typical instances that I have here, what I'm going to do for each of them, I'm going to solve for kind of the corresponding intervals, so the alpha intervals. And then I'm going to collect all of those alpha intervals and basically find the alpha intervals with the smallest empirical cost. That it tells me what parameter I should be using, but generalizes one. And how do you solve for these alpha intervals? Given an instance like this input here, how do I find the alpha intervals in an efficient way? So Travis has a cool idea of somehow doing a depth first search or an execution tree that somehow compactly describes all the possible merges over an instance as we vary alpha in the interval 0, 1. And if you're curious about this, I think it's a cool idea. You can read. There is an iClear paper on this in 2020. Okay, but the exciting thing is that actually now for this family of algorithms, we are able to run very large scale experiments. So what Travis again and Manuel Lang showed, basically like experimentally on large scale data, that, you know, like optimal parameters really do vary across different distributions. So we really want to learn the right parameter for your type of data. And choosing the right parameter can also give large improvements to the loss. So in particular, you can get large improvements over using the basic criteria like single linkage or complete linkage. So really, you can benefit drastically from learning the linkage criteria. Also, you can show this experimentally as well, not only analytically. Okay, cool. Now, so this is about clustering. Now, as I mentioned, you know, we thought about this area of data analysis design for a while now, and so we had many other case studies. So I'm just going to mention some of them here and tell you also some high-level insights about like analysis tools. So just a couple of, just I'm going to really mention them without going into the details here. So we also looked at alignment problems coming from CombBio or NLP. So here we consider parametric families of dynamic programming algorithms. And again, we asked the question of learning the best algorithms from the family for your type of data. We also looked at mixed integer programming, solving mixed integer programming via branch and bound techniques. These are widely used in operations research and AI. And you might want to learn how to branch or how to add cutting planes. We also looked at the problems, parametric family of problems coming from algorithmic game theory and economics, like, you know, learning how to price items, you know, maybe posted prices, two-part tariffs, and so on. And in fact, actually, and also recently with several of my students, we also looked at actually hyperparameter tuning in machine learning algorithms themselves, because also machine learning algorithms themselves have often hyperparameters, and we don't know how to. We have not known for a while how to prove them with how to tune them with provable guarantees. Okay, so these are just a couple of sample of types of problems we looked at, and Now you might, I want to mention actually, because that in a lot of us problems turns out that the following structure emerge, a very similar structure to what I had for linkage-based algorithms, but now more general, right? Because in linkage-based procedures, we only have one parameter. So the loss function, if I fix an instance of the parameters and vary the parameters, the loss function was one-dimensional. But if I'm trying to price items, I have many items, I have many more parameters, right? So now in general, kind of these loss functions maybe are high-dimensional, so more complex. But turns out that when you looked at all these case studies that I mentioned on this slide and many more, turns out that some kind of very cool structure emerged. So we're able to observe that in a lot of these problems, if we fix an instance of the problem and vary the parameters of the underlying algorithmic family, kind of the corresponding loss function is piecewise structured. So in particular, we can kind of partition the parameter space with some boundary functions coming from typically some function class, fixed function class F, such that inside each of the piece given by these boundary functions, kind of the corresponding cost function is structured. Again, maybe comes from some fixed family of functions G. And then turns out, that actually now we have this top 2021 results where we write this kind of generic theorem now. So if you have a data-driven algorithm kind of situation where your dual functions, this is what I call the dual functions, now is piecewise structured, we can tell you how many instances do you need to generalize. So we kind of decouple the statistical question of how many instances do you need to generalize from the structural properties of the algorithms family and the kind of corresponding problem at hand. So I would say that this is a very generic tool. If you have a new data-driven algorithm design problem and you're trying to understand the question, how many samples do I need to generalize? Then this is a very useful tool. Basically, what we show is if the corresponding dual functions are piecewise structured, we give you a precise bound on how many instances you need to generalize as a function of the structure, the given structure at hand. And it's yeah.
Can you
Yes.
say a bit, how does this fit into the clustering framework? So what are
Yeah,
these?
so in the clustering framework, the loss function was much simpler, right? So with the clustering framework, we had, let me go back to this picture. I have this picture here. This is the loss function that I had. In the clustering framework, we have this key fact that says if I fix an instance of the problem and vary the parameters, the cost function is piecewise constant with at most 10 to the 8 pieces. This was crucial in then proving that the pseudo dimension is not too large. The induced family of algorithms is not too large, so then I don't need too many samples to generalize. So this was kind of a crucial structure result that we proved for the clustering problem. Now, when we try to do the same exercise for other problems that I mentioned, like mixed integer programming, pricing problems, and so on, and we often basically the proof structure is very similar. We first try to understand some structural property of the algorithms family at hand, and it often look like if I fix an instance of the problem and vary the parameters, I'm going to have sharp transition boundaries, right? But I'm not going to have too many in a certain sense. Those boundaries will have some structure, and inside each of the piece, I'm going to have some structure. And then we then use that to then compute an upper bound on the pseudo dimension, like compute how many possible training instances you can have an exponential number of behaviors, which is what you need to understand what the pseudo dimension is, right? And we've done that basically for a variety of problems. So I've done it for 6, 7, 8 problems, basically from basic principles. And then the proof started to become repetitive. And then the question that we had, well, now can we write a generic theorem, right? So that if you have a new data-driven algorithm design problem, I'm telling you, just prove to me that if I fix an instance of the problems and vary the parameters, this cost function is piecewise structured. And we try to write this as abstractly as possible, right? When I mean is piecewise structure, I mean, I can partition the boundary, the parameter space with some boundary functions that comes from some family of boundary functions, a finite VC dimension, so that inside each of the piece, again, the cost function is nice meaning, well, it comes from a function class G that has, again, finite pseudo dimension, right? So try to write this as abstractly as possible. And then we give a bound. If the duals are piecewise structured, well, how many samples do you need to generalize? This theorem tells you how many samples you need to generalize. And basically for all data-driven algorithm design problems I worked with, you can apply this theorem, essentially. So if you're working, I don't know, social choice like Sivina does or something like that, and you're trying to do data-driven social choice, the first thing I would try to use is this theorem. Now I want to point out, doesn't lead to the tightest result. So we know some examples, so you don't necessarily get the tightest bound on the pseudo dimension, but it's widely applicable. And I think it's cool because it really decouples kind of the more statistical part from the structural part of the family of a hand. Did I answer a question?
Yeah, thanks.
Yeah, cool. All right. And so as I said, basically now a similar kind of proof ideas when we applied it, actually, like I already mentioned this to the variety of fields, like mechanism design, operations risk mechanism, mostly through like parametric family of revenue maximization pricing problems and auctions. In the branch and cut, like for solving mixed integer programs. In the recent years, we've done a lot of hyperparameter tuning in machine learning, like for example, learning to initialize the Lloyd's method or the classic K-means algorithm, learning the graph for graph-based semi-supervised learning, learning important parameters for things like elastic net and logistic regression, and so on. And also other examples that we had that are maybe more from theory of computing. Also, like for example, we learn how to run semi-definite programs, and so on. And so, like in a lot of these problems, basically, you can use this kind of, at this point, you can use the general theorem that I mentioned on the previous slide. Okay, cool. How many more minutes do I have? I guess, I can, okay, I guess I'm asking, okay, maybe I spent a couple more minutes to tell you that, and then I'll conclude. So this is statistical learning formulation of data-driven algorithm design. But, you can also consider maybe an online learning formulation, right? So in the statistical formulation, we assume that, the instances, the training instances are IID from some fixed amount distribution of our training instances and given to us up front, right? But what if the training instances are not given, are not IID, not given to us up front? What if they come online one by one? Well, of course, you can try to build on tools from online learning theory. And so what do I mean by this, actually, to be a little bit more concrete? So how does the interaction go? So first of all, before I might have to select an algorithm and I get an instance that I need to solve. I run my algorithm on the instance, A1 that I decided to use on the instance, and I observe how well I'm doing, right? And then the next day, again, I have to pick an algorithm. Then again, I'm giving an instance that I need to solve. I run the algorithm on the instance and I observe how well I've done, and so on. And basically, based on this kind of past history, then at any moment in time, I had to decide, my meta learning algorithm, my learning procedure has to decide what algorithm to use next. Gets an instance, observes, runs the algorithm, the given algorithm on the given instance, observes how well it's doing, and then, observes the cost and then keeps updating, right? And what do we want to achieve formally? Well, if we use an online learning theory, what we would like to achieve is to achieve no regret. So in other words, we want our cumulative performance of our learning procedure to be comparable. So if we look at the cost we incurred, has to be comparable to the cost of running just the best single algorithm from the family in hindsight on all the instances. This what means no regret in learning theory. Okay, so you can basically try to also use this online learning formalization to think about data-driven algorithm design now as an online learning problem. Now, again, the major challenges, sounds great, but the major challenge is, we know to do online learning. We've known how to do online learning only for nice functions like structured functions, like convex function, but as I showed you earlier, when the loss functions coming from data-driven algorithm design, they're not structured, they're not convex, they have many sharp transition boundary, they can be very wild. And so we couldn't just rely on existing tools from online learning theory. So basically we had to develop kind of new tools to basically achieve no regret guarantees. And in fact, if the instances are truly worst case instances, on no regret is not even possible, we proved, but we have this kind of cool Fox 2018 paper and some follow-up where we're able to identify kind of sufficient conditions on the loss functions that are sufficient for achieving no regret. So in particular, pictorially speaking, we're able to show that, sure, our loss functions might have sharp transition boundaries, but as long as, if we look back in hindsight over all our instances, kind of these sharp transition boundaries are not too concentrated, in other words, they are dispersed, then we are even able to prove that you can do online learning and basically do online algorithm selection with strong provable guarantees. Okay, so that's I know that this is too fast, but this part here might be a bit fast. But the bottom line is, if you're trying to use tools from online learning to think about online algorithm selection, it's not possible. You have to develop new tools, and there are some interesting subtleties because in the worst case, you might say, well, it's not possible to achieve no regrets. So, just I'm giving up on providing any provable guarantees. That's a bit boring, but we're able to kind of take a beyond those case analysis viewpoint, and we are able to show that, well, in the instances are somewhat nice, and the corresponding loss functions have dispersed discontinuities, and online learning is still possible with strong provable guarantees. Okay, cool. So to summarize, I'm going to use my summary slide here because I'm probably a little bit over time. I know it was a half-an-hour talk. So, data-driven algorithm design, I think it's an exciting field. It can overcome major shortcomings of classic algorithm design by adapting the algorithm at hand, the algorithm to the domain at hand. And this is well motivated. They have different methods, work better in different settings, on different types of data. And, if we have access to typical instances coming from our domain, it makes sense to learn an algorithm that works best for a given domain. And again, as I mentioned, this is widely used in practice these days, has been analyzed in the research community in the past 20 years. But up until very recently had no formal guarantees, and so our work basically helps lay data-driven algorithm design on solid theoretical foundations. We have a variety of case studies and also general analysis principles, like the two theorems I mentioned. So if the loss functions are the dual functions are piecewise structured, then you can give a bound on the sample complexity. That's an example of a general result, and also the general results for like online learning. And I'm a learning theorist, in addition to being an algorithms researcher, a theory computing researcher. And I think it's also super exciting that from a learning theory point of view, this line of work can also help us expand the frontiers of machine learning as well, right? So it's like we're learning more interesting objects than typically done in machine learning. We're learning algorithms that have modules, that interact with one another. The loss functions can have many sharp discontinuities that are volatile. So we really had to develop new tools. And so that helps us to really expand the frontiers of machine learning as well. And I actually want to mention that, I guess it would be cool if long-term this line of work. So at this point, as there's a question earlier, at this point, we hand design the family of algorithms we're considering, but, maybe one can lift that up a little bit, and maybe you can also, in a more automated way, generate such families. And it would be cool if long-term somehow this line of work, machine learning for algorithm design could lead to algorithmic paradigms as well as proof techniques of the types that humans are not able to design before. That would be really cool, right? I mean, that at that point you need to have to not hand design the family of algorithms anymore. And if you're curious, actually, I wrote a book chapter in this book on beyond use case analysis of algorithms in 2020. I summarized the work that was there at the time, but of course, this is a very fast-moving period. So we had a lot more work since then, and others had a lot more work since then. But if you, for an introductory point with mathematical details, you can read this book chapter that I wrote. And again, just to mention, because I mentioned several results with many of my students, for each of them, I try to put the names of the students, but here's also reference rights, because to acknowledge the collaborators as well. Thank you, and I'm happy to take more questions.
Thank you.
Let's thank the speaker.
Questions?
Can I ask about the setting with the online learning? So how should I think of the boundaries being, you said not too close to each other. Is this related to smooth complexity, like where you perturb the instance? And
yes, so it's a great question. So so what we are able to show mathematically, so first of all, like these loss functions now, are piecewise. We formalize as being piecewise, like piecewise Lipschitz loss function, right? Now, once you have sharp transition boundary, you can prove that online learning is not possible, even in one dimension. So you can just say no regret is not achievable. So it's a bit boring, right? I mean, you could stop there, but it's not interesting. And right. And so what we're able to show is that, well, if you look in hindsight and basically in any of let's assume that our parameter space now is Rn, so Euclidean space, right? If I look in any L2 ball, I don't have, not too many of my loss functions have sharp transition boundaries. That means that discontinuities, so the sharp transition boundaries are dispersed. I'm able to show that we're able to achieve no regret. And of course, it's with parameters, right? Because like there'll be your WK dispersed. If any ball of radius W, I have almost K boundaries, K sharp transition boundaries, and then the regret boundary depend on W and K and so on, right? There are parameters you put in there, right? So analytically, what we're able to show is like if not too many of the loss functions have many sharp transition boundaries in any small ball, you are able to achieve no regret. So this is kind of the first result. But now it's a great question, like how does this translate to data-driven algorithm design, right? So what we're able to show, for example, we're able to show for example, for linkage procedures that I mentioned, the alpha-weighted linkage procedures, like when will you get dispersed boundaries, right? Like under what properties of the input data will the corresponding loss functions have dispersed boundaries? Okay, and it turns out that actually indeed you are right. So basically, one example we show for linkage family for clustering and linkage-based procedures. Well, if the input instances are a little bit smooth, right? So basically, there's been a bit there's been a bit of noise added to the distance function. Then we're able to show that these sharp transition boundaries are dispersed. So we are not too concentrated, and so then indeed we are able to achieve no regrets. So it's kind of a sufficient property of the input instance that leads to dispersion in the loss function space.
I see, thank you.
But there could be other situations, right? But that's a sufficient condition. And it's one that we analyze in several works, including in clustering.
I see. Cool. Thank you.
In the interest of time, I propose to delay for the questions for the informal discussions. So we thank Nina again, and we move on. And thank you. And the next speaker is Karol Zamfirescu from Ghent in Belgium. And he's going to be talking about conjecture of Grunbaum and key to hypohamiltonian